This PowerPoint discusses electricity. First thing we want to talk about with electricity is current. Current, we use a capital I in order to designate current, and current is the rate at which charge is flowing through a circuit. The units that we use is going to be coulombs per second, because the rate of anything that's flowing, rate is going to be dividing by seconds, and the rate of charge is going to be coulombs per second. And we simplify that by calling that amperes. Now, since every electron has a specific amount of charge, 1.6 times 10 to the negative 19th coulombs, you can think of current as the number of electrons that are passing a single point in a given second. So let's say you stop and you look at a current, look at a wire with a current going through, and you count the number of electrons that pass by. Well, that's essentially the same as determining the current. Now, that's not the same as how fast the electrons are moving, because how fast the electrons are moving is a little bit different. So each electron does not move from the beginning to the end at the rate of the electricity. Essentially what you have is you have the electrons that are bumping into each other. So when the battery releases an electron, that electron then bumps into another electron, passing its energy along, and then that one passes its energy along to another one, and it keeps bumping along. And the rate of electricity is the rate at which that energy is moving through the system or through the circuit, not the rate at which the electron is moving. The speed at which the electron is moving is actually referred to as drift velocity. It's a lot slower than the rate of electricity. But if you want to get an accurate reading on electricity, basically you're looking at one point and counting the number of charges that pass that are essentially bumped by that point in order to determine the rate of charge in a circuit, which is going to be the current. Next, we're going to talk about the junction rule. That's Kirchhoff's first law. Now, you don't really need to know that this is Kirchhoff's first law, but you do need to know the concept that current is conserved in a circuit. So basically, the amount of current going into any point is going to be equal to the amount of current coming out of that point. So if we got a straight line, it's pretty easy. It's pretty easy to see that the current coming into this single point is going to be equal to the current coming out, because current is not created or destroyed. Current is the rate at which the electrons are flowing, and we don't create or destroy electrons in a circuit. So the amount of current going in is going to be equal to the amount of current coming out. Where it gets a little bit more complicated is something like this, where we actually have a junction, and that's why it's called the junction rule, is we got current coming into this junction, then the junction splits and current goes up and down, so the amount of current going into that junction is going to be equal to the current coming out. So I1 equals I2 plus I3. Next is voltage. Voltage is the average amount of potential energy per unit of charge in the circuit, and basically this is the potential energy that the charges are carrying with them as they go through the circuit. The units is going to be joules per coulomb, which is converted into units of volts. This unit of voltage is also referred to as potential difference, because essentially what we're talking about the electrical potential difference from one side of the battery to the other. Now in my head, when I visualize a circuit, I'm basically thinking of little green guys that are running around, little stubby arms and stubby legs, carrying a box with all this energy in it. And basically the electron represents the little green guy and the box of energy, and they have to pull that energy out as they're going through the circuit. Now the amount of energy they start with is given by the battery, and every electron has the same amount of energy. So when we talk about the voltage, we can talk about the amount of energy each electron is carrying. Since the electrons have a set amount of charge, then we'd say the potential energy per unit of charge. We can also say the potential energy per electron. And we can think of this as voltage when we're talking about the amount of potential energy. So the potential energy is actually caused by the negative end of the battery pushing the charges out and the positive end pulling them in. So essentially what the wire does, it takes the electric field and confines it to one narrow stream, so the electrons follow that stream and they're basically pushed out one end and pulled in the other. So the electric field goes through the entire wire at the same time. The question comes up, how does the battery know that there's one light bulb or two light bulbs, or knows that it's lighting at the same time? It's because the electric field going through the entire wire at the same time sees both of those light bulbs at the same time, which is why it lights both of them rather than lighting one and then lighting the other. Now, since voltage is the potential difference from the positive end to the negative end of the 9-volt battery, and that's 9 volts, then that means the electrons are going to lose 9 volts of energy per unit of charge from one end to the other, from the negative end to the positive end. Now you can think of that of gravitational potential energy. Gravitational potential energy, let's say for example you got 3 objects that are up here, 1, 2, and 3, and they're going to all fall down to below these words right here. Well, whether this object goes up and then back down, or this object here goes sideways back back and forth as it goes across the screen and gets down to the bottom, or this one goes straight down to the bottom. Basically what you're going to see is you're going to see that they all start at the same height, they all end at the same height, and if they all have the same mass and the gravitational field is the same for all of them, then they're all going to have the same change in gravitational potential energy. It doesn't matter how they get to the bottom, it doesn't matter what path they take to get to the bottom, they're all going to have the same change in gravitational potential energy. Well, it's the same way with a circuit. In a circuit, you get the same change in electrical potential energy as well. And for a 9-volt battery, the electrical potential energy is going to go 9 joules per coulomb of charge, and and every electron that goes through the circuit is going to lose that voltage as it goes through. All right, the loop rule. This is Kirchhoff's second law, and again, you don't need to know that it's Kirchhoff's law, but what you do need to know is that energy is conserved in a circuit. Now, this is a different type of conservation of energy. When we talked about conservation of energy before, we're saying that a system is closed and no energy comes in and no energy goes out. When we're talking about circuits, conservation of energy, this conservation is a little bit different. Basically, when we're talking about conservation of energy, we're saying the amount of energy coming into the system produced by the battery is equal to the amount of energy leaving the system produced by heat or light or whatever the resistors do in order to dissipate that energy. So in this conservation of energy, the amount of energy in equals the amount of energy out, but it's not a closed system like when we talked about conservation of energy before. So basically we have our circuit and we have a voltage supply here, and that voltage supply is going to give the electrons the energy that they need to go around the circuit. But as the electrons go around, they lose that energy. So we're going to look at the voltage as compared to the resistors as it's going around. Now when the electrons go through the voltage source, it picks up potential energy, and then it loses that potential energy through the first resistor, the second resistor, and then the third resistor to the point of where it gets back to the original voltage. So at any point along this path, we can take a point here and look at its potential energy. When electrons go around, the potential energy when it gets back to this point is going to be the same. So the total change of potential energy from at any point in the circuit is going to be constant. So the amount of potential energy that the electrons lose and the amount of potential energy the electrons gain is going to be balanced, so the electrons are always gaining and losing the same amount. And that's how we get Kirchhoff's loop rule, that any loop, the total energy that is put into the system and taken out of the system is going to be conserved. Resistance is the amount in which flow is hindered, and basically it's measured in units of ohms, and that's a Greek letter omega used for the units. Now there are 4 categories that we kind of put materials into. The first category is superconductors as far as resistance is concerned. Superconductors are very, very, very low resistance. Usually these are certain types of materials that are very, 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 very cold temperatures. There's little to almost no resistance at all. And basically what happens is that those cold temperatures allow the ambient heat and energy to kind of settle down to almost nothing, to where the electrons pass through and the material doesn't hold on to the electrons very, very much. And that's basically what determines how much resistance a material has, is how much it holds on to the electrons tightly. So at very cold temperatures, it's not holding on to the electrons, so the electrons can pass through really easily. The next step down is going to be conductors. Conductors, they hold on to their electrons some, but they allow them to pass a little bit easier than other things, but not as much as superconductors. And these are your types of materials like copper and gold and silver, and those metals that allow electrons to pass through fairly easily, but it does offer some resistance. The next is semiconductors, and these allow some electricity to pass through. This is more of like your silicons, like the computer parts in your computer that are made out of silicon in order to allow an electrical current to go through, but not a lot of electrical current, because if too much electrical current goes through, then basically it's going to fry your motherboard. There are some sensitive materials on your computer that if too much electricity passes through, it's not a good thing. So the semiconductors are intended on letting just a little bit of electricity pass through. And then you have your insulators, which allow little to no electricity to pass through. Now, the air you're breathing, that's a great example of an insulator. Now, just because something's an insulator doesn't mean electricity can't pass through it. If you think about air, a lightning storm can send a bolt of lightning through air because there's enough voltage between the cloud and the earth that it'll push that electricity through, and that insulator can actually allow electricity to pass through. It's just very, very difficult to do so. So now this brings us to Ohm's law. Current is the balance between voltage forcing the flow through and resistance hindering the flow. You can kind of think of it as a car that's driving down the road at a constant speed. The wheels and the engine are pushing that car forward, but the air resistance is pushing back on it to where those two are balanced, and the flow of the car, or how fast the car is moving, is equal to the flow of the electricity, where it's moving at a constant speed. So if you think of voltage, increasing the voltage will increase the current. This is referred to as a direct proportion. Direct proportion means if I double the voltage, I'm going to double the current. Resistance, however, is referred to as an indirect proportion. An indirect proportion means if I have double the resistance, then I'm only going to have half the current. So that's an inverse relationship. Now this simplified is going to be equal to V equals IR. And that's usually how Ohm's law is written, is voltage is going to be equal to current times resistance. Alright, so let's suppose we got a 9-volt battery that was lighting a bulb with a resistance of 3.0 ohms. What's the current through the light bulb? Well, if you need to find the current, the voltage is going to be equal to current times resistance. So to find current, we divide by resistance, and the voltage divided by resistance is going to be 9 divided by 3, which is going to give us 3 amps. The next example says, suppose a 3.5 volt power source is produced a current of 0.50 amps through a resistor. What is the resistance? Again, voltage is going to be equal to current times resistance. So to find the resistance, we got to divide by current. So voltage divided by current is going to be 3.5 divided by 0.5, which is going to give us 7 ohms. And dividing by 0.5 is the same as multiplying by 2. Dividing by a half and multiplying by 2 is the same thing. So 3.5 times 2, that gives us 7 ohms. The next one says, suppose a 2.5 ohm resistor has a current of 1.5 amps through it. How much voltage is the resistor using? So voltage is going to be equal to current times resistance, and 2.5 times 1.5 is going to give us 3.75 volts. Alright, power is going to be the rate at which energy is used. Now we've talked about power before. Power in a resistor or a battery is going to be equal to the current through that object times the voltage either used or supplied by that object. So power is equal to current times voltage. Current is coulombs per second. Voltage is joules per coulomb. And you can see that the coulombs are going to cancel, which is going to give us joules per second. And that gives us our watts that we need when we talk about power. So with a light bulb, this relates to how bright the light bulb shines. The more wattage it is using, the more power it is using, the brighter it's going to shine. So what's the current through a 60-watt light bulb if your house receives 120 volts? Well, power is going to be equal to current times voltage. In order to determine the current that's going to be through it, then we're going to take the power and divide by voltage. The power is 60 watts divided by the voltage, which is 120 volts. 60 divided by 120 gives us 0.50 amps for the current.